In my previous video, I used commonly available materials to do photolithography on silicon. Today, I'm going to combine photolithography and one of my all-time favorite chemical reactions to create the conductive metal wires used to connect devices in an integrated circuit. I've already talked at length about the development of the integrated circuit and how humanity went from being able to produce a single transistor to billions of transistors on the same chip. However, billions of unconnected transistors on their own won't do anything unless we can wire them together in a circuit. A cheap, reliable, and scalable method for producing metal wires on the surface of a silicon chip is therefore a top priority in integrated circuit fabrication. To accomplish this task, we want to deposit a layer of solid conductive metal, such as aluminum, copper, silver, or gold, and then use photolithography to remove the metal that we don't want, leaving behind a bunch of thin wires that connect individual devices together in a circuit. There are two common ways to accomplish this task. The first is an etching process. In this process, you deposit a layer of metal onto the chip and then apply photoresist over that. Then you expose and develop the resist, which removes portions of the photoresist layer. Then you immerse the chip in an etching solution that dissolves the exposed metal, leaving behind metal only where the photoresist is still protecting it. Then you immerse the chip in a solvent that dissolves the photoresist, which gives you your final product. The second method is called liftoff. In this method, you put the photoresist layer down first. You again expose and develop the resist, which removes portions of the photoresist layer. Then you deposit metal on top of that. Notice that the metal layer sticks to the whole surface, regardless of whether the surface is the chip itself or the photoresist layer above. Then you immerse the chip in a solvent that dissolves the resist. As the resist dissolves, any metal on top lifts off the chip and is carried away. The metal that was in direct contact with the chip is unaffected by the solvent and sticks around, giving you your final product. Now, regardless of which method we choose, we still need some way of depositing an even layer of metal on the surface of a silicon wafer. In modern semiconductor fabs, metal layers are deposited onto the surface of the chip in a process called thermal evaporation. This process is carried out in a vacuum chamber, and a small sample of metal is heated until it vaporizes. Just as boiling water produces steam, vaporizing metal produces a cloud of metal particles, which condenses or deposits onto the surface of a chip in a smooth, uniform layer. This process is nice because it's reliable, controllable, and clean. The downside of this process for the hobbyist is that it requires the construction of a dedicated machine with expensive parts in order to make it work. It would be nice if a method were available to produce conductive layers on a chip without the need to spend a bunch of time and money building a thermal evaporator. I sat down and thought about the problem for a while and realized there might be an easier way. Whatever method we use needs to meet the following requirements. First, the layer needs to be conductive. Traces ideally should be less than 10 ohms or so. Second, the layer needs to be durable. Traces shouldn't fall off or deteriorate over time. Third, the process needs to be reliable. We don't want to have to try over and over again to get good results. Fourth, the process needs to be quick. We don't want the step to take too long or it will dramatically slow down the whole fabrication process. Fifth, the process needs to be compatible with photolithography. Otherwise, we won't be able to create accurate connections to devices on the chip. And last, the process needs to be as cheap and easy as possible. Otherwise, it's better to just spend the time building the thermal evaporator. My first idea was to use conductive paint. I think most hobbyists who have played with circuits have probably seen stuff like this. Little pens that dispense ink that contains enough graphite or silver particles to conduct electricity, allowing you to literally draw circuits on paper. Most conductive paint is designed to be applied to paper and not glass, silicon dioxide. However, I did find this product from Permatex. It's a conductive paint used to repair vehicle defoggers. If you've never noticed them, they are those little metal wires you see on your rear window. Electric current is passed through them and it causes those wires to heat up, which heats the glass and defogs your window. What's nice about this product is that it's specifically formulated to stick to glass. It's a bit expensive, about $20 for this tiny bottle. I tested it on a microscope slide and used tape to make a small line about 5 centimeters long and a couple of millimeters wide. I tested its conductivity with a meter, and I was pleased by the results. However, I realized a major problem. This paint is not compatible with our photolithography process. I exposed the paint to acetone, which is used to strip photoresist, and it came right off. I also tested it by exposing it to developer solution, and while it was a little bit more resilient, it still weakened the paint to such a degree that it rubbed off quite easily. I could have tested other paints, but I'm fairly confident that other types of conductive paint will suffer the same problems with solvent resistance that we saw here. This means that this method is probably not suitable for making chips. I also briefly considered conductive epoxy. Unfortunately, all of the conductive epoxy I found required long cure times, hours or days instead of minutes. It also can't be easily etched away, and I suspect it will probably not work too well with liftoff either. So it's probably not very compatible with our photolithography process. Moving on. A chemical process was my next idea. One of the most common chemistry demos in high school is the silver mirror reaction, which produces a thin layer of silver on glass. The silver mirror reaction requires the following chemicals. Sodium hydroxide and ammonia are readily available from hardware stores, and silver nitrate and glucose are easy enough to find online. Rather than working out the math myself, I'm going to use the same formulation I found in a chemistry demo kit. It calls for the following solutions. First, we prepare a 0.6 molar solution of silver nitrate. That corresponds to 1 gram of silver nitrate and 10 milliliters of distilled water. The solution is light sensitive, so I'm storing it in an amber vial. Do your best to keep it out of direct sunlight. Next, we need a 2.5 molar solution of sodium hydroxide. That is, coincidentally, 1 gram of sodium hydroxide and 10 milliliters of water. Make sure to add the sodium hydroxide to water and not the other way around. Sodium hydroxide can heat up a lot when it dissolves, so go slow and be careful. Now we need a 2 molar ammonia solution. This ammonia is 10%, which is about 6 molar, so I used 1 part ammonia and 2 parts water for my solution. Lastly, we need glucose. Note that you cannot use regular table sugar for this reaction. It has to be glucose specifically. We need a 10% glucose solution, which is 1 gram of glucose plus 10 milliliters of water. Shake until dissolved. I've labeled each vial and also labeled a pipette corresponding to each chemical so I don't accidentally contaminate them. Alright, I think I'm ready to see if this works. The procedure is simple. We start with 5 drops of the silver nitrate solution, then we add 3 drops of the sodium hydroxide solution. This causes the silver nitrate to react and form silver oxide, which forms this dark brown precipitate. Next, we add 15 drops of the ammonia solution and swirl or shake the vial. This forms an ammonia complex that dissolves back into the solution. Last, we add 2 drops of the glucose solution. This is actually my first time seeing this reaction happen in person. The solution started out clear, but quickly developed a slight dark tint as small amounts of silver precipitated out of solution. I slowly twisted the vial in my hands in order to distribute the small amount of solution as evenly as possible on the walls of the vial. After about a minute, it became obvious that some kind of coating was developing on the inner wall of the vial, and after about 3 minutes, that coating became a brilliant silver mirror. I was honestly impressed it was this easy. I ran the test several more times and never had any issues with the reliability. It just works. Once I was satisfied that the solution was used up, I needed to deal with the liquid remaining in the vial. Apparently, you should make sure not to let the solution dry out, as it is possible for it to form silver fulminate, an explosive compound. Now, I seriously doubt the amount I have is any danger, but just to be safe, I'm going to pour it into a solution of sodium chloride. Once that's done, it can be safely disposed of. And there we have it. A nice silver coating on the inside of our vial. Since it's opaque, it's got to be at least 100 nanometers or so thick, but I have no real way to measure its thickness accurately. Now, silver is a fantastic electrical conductor, but this silver layer isn't solid. It's actually tons and tons of tiny particles all stuck together. It should be electrically conductive though, so let's measure that. Good news, I'm reading a resistance of less than 1 ohm on this piece of glass, so it's definitely conductive. Alright, now let's see if we can get a good layer on this silicon chip. I grew an oxide on it and made sure it was nice and clean. I prepared the silver solution and added it to the vial along with the chip. I shook the vial to distribute the solution in an attempt to evenly coat the chip and, once again, waited about 3 minutes for the silver mirror to form. Once that was done, I extracted the chip and washed it with distilled water and dried it. Wow, I clearly damaged the chip from all that shaking. It's missing chunks out of the corners, but at least it's coated relatively evenly. and the layer is indeed conductive. The only problem is that the coating is not adhering super well. It's pretty easy to rub the silver layer off with something like a paper towel. Maybe we can make it stronger by annealing it in the tube furnace. I put the chip in my quartz boat and slid it into the furnace a few times at various temperatures, from 500 Celsius to 1000 Celsius, to see if it had any effect. It's hard to tell, but I think the higher temperatures did improve the durability slightly, but when I went back and tested the resistance, the silver layer was no longer conductive. I found this odd because silver is a noble metal and doesn't really react with oxygen or nitrogen in the air, even at high temperatures. Unlike metals such as iron or aluminum, which readily react with air to form oxides, silver compounds actually decompose at high temperatures back into silver metal, so it's not really likely that this layer is anything but pure silver. So why is it no longer conductive? I scratched my head for a while trying to figure this one out, and eventually found this research paper that gave me the answer. Thin silver layers, when heated, bead up and separate into a bunch of tiny silver dots. They are still elemental silver, but since they are no longer connected to each other, they cannot conduct electricity. This effect happens even if the silver is heated to temperatures well below its melting point, which means that we cannot use the furnace to anneal the layer without risking the layer becoming non-conductive. This is a bit of a disappointment, but as long as we're careful not to scratch the silver layer, it should still be durable enough for our purposes. Now that I was sure I could use this chemical method to create a usable silver layer, I charged ahead and attempted to combine it with photolithography in the liftoff process described earlier. This is the one where you apply the photoresist first, and then the silver layer on top of that. I applied the photoresist to the chip using the laminator, and then exposed and developed it using the same mask from the previous video. Once I verified the chip was clean, I went ahead and prepared the silver solution as before. This time though, I used twice as much, just to make it a little easier to swirl and ensure it actually gets all over the chip. I mixed the silver nitrate, sodium hydroxide, and ammonia solutions first, then put the chip in, then added the glucose to start the reaction. It was right about here that I started realizing that something went terribly wrong. 3 minutes later, I once again got a beautiful silver mirror and extracted the chip when I realized I had made a serious mistake. The photoresist was completely gone. What happened? Here's the problem. The developer solution is sodium carbonate, and if we measure the pH, it's somewhere between 10 and 11. I measured the pH of the silver mirror solution and found that it had a pH of at least 12, which is no surprise considering that sodium hydroxide and ammonia are strongly alkaline. We know from the previous video that basic solutions will damage the photoresist over time, and it looks like the pH of the silver solution is high enough to cause the photoresist layer to disintegrate completely. I had a moment of panic because I thought this meant that the whole project was dead in the water. Then, I realized that the situation wasn't quite as dire as I had feared. Yes, the silver plating solution is incompatible with the photoresist, but that just means that we can't apply the silver after we apply the photoresist. We can still apply the silver before. This means that we can't use liftoff, but we can use the etching method. In order to make this method work, we'll need to develop and test an etching solution for silver. Fortunately, I have just the thing. These are the vials left over from all the previous reactions. I can use them to test any etching solutions we come up with. Speaking of etching, we sort of backed ourselves into a bit of a corner. You see, the fact that silver is a noble metal means that silver much prefers to be an element instead of a compound. This is why our silver mirror reaction is so easy. It takes very little persuasion to convert the dissolved silver ions back into elemental silver metal. However, this means that the reverse, converting the silver metal into silver ions, is hard. Even strong acids like sulfuric and hydrochloric acid alone won't do the job. The usual method for dissolving silver is to use nitric acid, but I don't have any of that. Fortunately, there is a cheat code when it comes to acids. You can add a small amount of peroxide to an acid to allow it to react with metals that it normally wouldn't be able to. I added about 10 milliliters of concentrated sulfuric acid to about 10 milliliters of 12% hydrogen peroxide, making a slightly diluted version of something called Piranha Etch. This stuff will react aggressively with organic material, so it's important to keep yourself safe and protected. I poured the Piranha solution into the silver vial and waited. It does indeed strip the silver off, but it's not exactly what I'd call a nice or even process. It seems like the silver is sort of flaking off in an uncontrolled manner. I tried the same thing with hydrochloric acid and peroxide, hoping for better results, but the outcome was exactly the same. Just this slow flaking of the silver layer. It took a bit of thinking, but I realized the problem. In order for the silver etching process to work, you need two different things. First, you need the etchant to react with the silver, and second, you need the product of the reaction to be soluble. You see, when we reacted the silver layer with sulfuric acid and hydrochloric acid, the silver converted to silver sulfate and silver chloride respectively. Both of these compounds are insoluble in water, so the surface silver atoms reacted, but they didn't go into solution. Instead, they just stayed there, blocking the remaining silver atoms from reacting. If instead we chose an acid that produced a soluble silver compound, the silver would react and then dissolve, going into solution and exposing the remaining silver, allowing the subsequent layers to react, eventually removing all of the silver in a reliable fashion. This is why nitric acid is the preferred etchant for silver. Here's a list of silver compounds sorted by solubility. You can see here that silver nitrate has an insane solubility of almost 3 kilograms per liter of water. The next on the list is silver fluoride, so it's possible that we could use HF to etch the silver. However, we really shouldn't be using HF for anything we don't absolutely have to. Well, the next compound on the list is silver acetate, which is just about 2 orders of magnitude less soluble, about 11 grams per liter of water. Still, this might just be enough, and better yet, silver acetate is formed by acetic acid and peroxide, which is a much less scary combo than hydrofluoric acid and peroxide. I stole some vinegar from the kitchen, which is about 5% acetic acid, and I mixed it with an equal amount of 12% peroxide, and poured it into one of the silver vials and waited. Hey, that's more like it. The etching process is much quicker and a lot more consistent than with either the sulfuric or the hydrochloric acid. Just goes to show that sometimes the best solution is not the strongest chemical, but the right chemical. I used my hot plate to warm the vinegar peroxide solution to about 50 Celsius, and the results were even better. The silver layer was stripped bare in only a few seconds. Looks like we've found a suitable etchant for silver. Now that we have our etchant, let's try the photolithography again, using the etching process. I once again prepared the silver mirror solution and added my silicon chip. This time, to avoid damaging the chip, I'm using a narrow vial and rocking it back and forth, rather than shaking it to pieces like last time. This method has the added benefit of allowing you to see what's going on as the layer deposits, assuming you're careful and don't rotate the vial. I rinsed and dried the chip, and once again peeled the protective plastic layer off the photoresist and ran it through the laminator. I made a new mask that is just 3 traces, or wires, of varying width to more quantitatively test the resistance of the silver layer. Looks like the exposure was successful. Now I just need to remove the final protective plastic layer from the photoresist and develop it. Wait a minute, what just happened? Well, there's the problem. Instead of peeling the protective plastic layer off the photoresist, everything, the plastic, photoresist, and silver layer, peeled completely off the chip. It looks like the silver layer is not very well adhered to the silicon dioxide surface of the chip. I thought this might just be a cleanliness problem, so I tried again several more times. I tried baking the chip to remove any traces of moisture adsorbed to the surface, as well as using Piranha solution to destroy any trace of organic material like oils that might have been a problem, but nothing worked. Each attempt produced the exact same results. Now, I'm sure that some of you are yelling at your screen telling me I have to use a plasma cleaner, and that probably would help, but sadly I don't have one. Also, even a pristine surface wouldn't really improve things very much. The reason for this is that silver just doesn't adhere well to silicon dioxide. Period. This is one of the reasons that silver isn't very commonly used to make integrated circuits, even though it's the most conductive metal. When the need arises and silver absolutely has to be used, it's often deposited on top of a thin layer of something else that has better adhesion to glass. Really, the main problem here is the photoresist itself. The photoresist I'm using is a very thin layer in between two pieces of protective plastic. Unfortunately though, this plastic layer is sticking to the photoresist better than the silver is sticking to the chip, causing our silver layer to delaminate. Now, it's tempting to just remove the plastic at the start of the process, but without the protective plastic, the photoresist will surely be destroyed when it runs through the laminator. Curses! If only the manufacturer had considered my ridiculous out-of-spec use case for their product and designed it better. If only the plastic layer were something more slippery. Something like... Wait a minute. Actually, there's nothing stopping me from replacing the clear plastic layer with a more suitable material. And I know just the thing. PTFE, or Teflon, is extremely slippery because of its carbon-fluorine bonds, and it's readily available as thread sealing tape. Let's see if this works. I used tape as normal to remove the first piece of plastic from the photoresist. Then I stuck another piece of tape directly to the edge of the photoresist and peeled the second layer of plastic off, leaving me with the very thin, fragile resist layer only. I placed that on top of the silver layer on a new chip and carefully applied the Teflon tape, then used a piece of index card to encase the whole thing and ran it through the laminator. Well, it was a little tricky, but I did manage to separate the PTFE from the photoresist without peeling the silver layer off. I found that it helps to turn the temperature of the laminator down slightly. Don't turn the temperature too far down though, or you'll get bubbles like I did in this other chip. This one should be fine though. I once again exposed the photoresist and developed it as normal. Now it's finally time to use the silver etching solution. Man, that is so satisfying. The results are excellent. Now that the silver layer is gone, we just need to remove the remaining photoresist with acetone. This is the last step, and I'm basically holding my breath at this point, hoping I don't run into any more problems. Fortunately, the photoresist layer separated and the silver remained undamaged. I checked the resistance of each of the traces with a multimeter. It looks like the narrow trace is about 20 ohms, the medium trace is about 10 ohms, and the fat trace is 5 ohms, which I think is acceptable for now. I might be able to tweak the process and get a thicker silver layer for better conductivity, but I'm not going to bother right now. What is bothering me is the durability of the silver layer. The probes aren't really sharp, but they are more than enough to scrape away material from the landing pads I made. You know what? I think I have just the thing to fix this. Remember the conductive paint from earlier? Well, it may not work with photoresist, but I can still paint it on manually to protect the pads a little. That was a little sloppy, but nothing an X-Acto knife can't fix. Let's see if that makes an improvement. Well, it's not perfect, but it's clearly protecting the silver layer a little bit. In the future, I'll have to do more tests and see if something like conductive epoxy would be a better choice for this. For now though, I'm pretty satisfied. The last thing I want to do is test the resolution of the process. I used the mask from the last video and ran through the same process of depositing the silver, doing the photolithography, and etching the silver away. The results look great. I don't really see any major issues with undercutting. I expect that the resolution of the metal layer is limited by the photolithography, which is what we want. Well, I think I've set a record for the number of nearly insurmountable problems that I had to overcome to make this process work. But work it does. I made a bunch of copies of the chip, and the results were all pretty consistent. I'm sure there is work to be done in the future to improve the process, but I'm going to call this here. I'm very pleased that I was able to make metallization work using a simple chemical process that requires no fancy equipment whatsoever. I think in the future I'll still want to make a thermal evaporator for increased flexibility, but for now, this silvering process should suffice. I just want to thank everyone for making it to the end of this video. I also want to thank everyone who emailed me after my last video with photoresist information. I'm making some good progress on that front, and I'm super excited to share it soon. I also want to thank my patrons who funded this project and bought all of these random chemicals. Thank you so much. I'll see you next time.